officially, and I'm going to share the whiteboard with you. Please ensure that you can see my whiteboard. I hope that you can see my whiteboard. Okay, don't annotate on my screen. Okay, so anyways, we talked about deviations, and deviations are often calculated by the tool which is called variance, you know very well. And this is the tool that we use to calculate the deviation. And variance has its counter, another form, that if I take variance, the positive square root of the variance, then we call it as standard deviation. So these are all the measures of deviation. Other than this, various other deviation measurements are there. Say, for example, range is there, mean deviation from mean is there, mean deviation from any central tendency point is there. But this is the, these are the two formulae that actually are mostly used, and I can pretty much logical, mathematical, and therefore it's mostly used, this variance measure to measure the deviation. But the question is, using variance, what do we measure? What sort of deviation we measure? For by variance, we can find the mean of this continuous, since deviation is measured with respect to this central pillar. And we know that variance is actually given by this formula, x minus ex whole square, and it has an operational formula which is expectation of x squared minus expectation of x whole square. We know this. We have discussed this particular thing many a times. Now suppose instead of this kind of single variable, single discrete variable x, we have two random variables x and y. Okay, now you can do three things to the given system. Suppose this random variable x is the price of some product at different times, and capital Y may be the demand of this product at different times corresponding to each prices. So suppose you have a random variable where you have a system where two random variables are there. Such a system is actually called a bivariate system. Bi means two, and since there are two random variables, we call it a bivariate system. Now the probability distribution of the bivariate system will be explained later on, but I'm not going to the details of that because it is a matter of subject matter of module 3. I am just trying to concentrate on the topic that I have mentioned in the beginning of the class. That is the most important part. Now, what we can do with this particular set of observations is the following. We can measure three quantities. Say, for example, number one, we can measure deviation of x from ex. We can measure it, and we know that for this particular measure we shall use the tool which is called variance of x. What else we can do? We can measure deviation of y from the mean, that is expectation of y, and you know that this is given by the measure called variance of y. We can do these two operations on the given system. What is the third thing that we can do on the given system? We can calculate mutual deviation of x with y. So by mutual deviation, I actually mean that how one of the variables vary if other variables changes. Say for example, we know that if x is the price and y is the demand, then if price changes, demand also changes. Okay, say for example, x is height and y is weight, and if the person is not a glutton, then if height increases, weight also increases. Say for example, if we can consider the income and expenditure, income and when when price increases, demand decreases, and when income increases, expenditure also increases. And you can put various instances where two variables can move simultaneously. So by mutual deviation, we actually mean how the one variable changes with respect to the other variable. That quantity that I am going to discuss in my part in this particular class, and I'm going to talk about the tool that can be used to calculate this mutual deviation. So this number 3 is actually different from number 1 and number 2. Number 1, the point ex and point ey in number 2, they are fixed. The pillar is fixed, and we are actually trying to find out how the points are scattered around them. But in point number 3, we are trying to consider, say, this variable and this variable, and I'm going to consider how they are deviated from one another. Or say for example, I'm going to consider this point to that point, and then I'm going to measure this particular deviation, or this point I can consider, or this point I'm going to take the measure of this particular thing. But don't worry that suppose there are infinitely many points, and then it is not possible for us to consider each point and each pair one at a time and trying to find out their deviation somehow. There is a very well versed mathematical formula which can be used over here, and this tool that we shall be using over here is actually called this is actually called the covariance. Covariance means the covariance, you can say it in this you can put it in this manner, the covariation of x and y. They are there is a kind of movement of the two variables, simultaneous movement of the two variables together, because it happens in the bivariate case. Two variables move simultaneously. One decreases, so one increases, or it may so happen that both of them are increasing in increasing direction, or both of them are in decreasing direction. So this simultaneous movement is there in the two variables. Covariance means they are mutual variance of the two variables and mutual deviation of the two variables, and we actually write it in the following manner, that covariance between x and y. So we put it in the following way, covariance of x comma y. What is the formula that we can use to calculate the covariation is the following. The formula is given by expectation of x minus ex multiplied by y minus ey. Okay, so this is the general formula with which we actually calculate the covariance. If you want to see the formula without looking into it through the lens of expectation, then in basic statistics, this particular covariance can also be expressed in the following manner. We divide by entire thing by the total frequency, and we consider each and every point, and we try to find out this quantity, xi minus x bar into yi minus y bar. So if you are not doing it from the viewpoint of expectation, this formula you are going to use to calculate the covariance. Okay, and if you are going to use the covariance formula with respect to the expectation, then you have to stick to that formula. And once I told you that you can always think of from a pedagogical point of view that this formula is actually reflecting this one, and this formula is actually reflecting that one. Now, probably you are thinking that, okay, it's quite, I mean, we are not able to grasp the idea about how to calculate the covariation. Is there any operational kind of thing? I mean, you know that variance is actually defined, usually defined by this formula, but we could use this result also. We can deduce this result from this one to calculate the variance. It is often helpful. So is there any such thing that we can do with the covariance? The answer is yes, we can do it. We can give an operational, we can represent an operational formula which can be deduced from the original one. So what is the operational formula that we often use in terms of expectation? It's very simple to deduce. I'm going to show you. What you first do is that we first multiply the terms term by term. So for example, we will multiply xy, and then we will multiply with x the quantity expectation of y. Then we will multiply by y with the quantity expectation of x, and then we are going to multiply the two expectations together, expectation of x into expectation of y. I'm going to write in the next page. So this is the thing after multiplication. Now, okay, I can do one more step over here. Now what is happening, you see, you already know that from the property of expectation that we can say that if there are two random variables x and y, then expectation of x plus y and x minus y is given by expectation of x plus minus expectation of y. You already know this rule, and it is independent of, it is irrespective of what variable you are taking. Is in be it independent or not, doesn't matter. So we can think of this as one variable. It is a random product of two random variable is a random variable. This is also a kind of random variable. Why? Because see, expectation of y is nothing. Y expectation of x is what? Mean, and mean is always a constant quantity. It is a constant number. So actually what you are getting over here, a constant quantity is getting multiplied by the random variable. So it is also a random variable. This is also a random variable. And these are the constant quantities. So we can use this formula and we can write it in the following manner. We can write it as expectation of xy minus expectation of x into ey and minus expectation of y into ex and expectation of x multiplied by expectation of y. Okay, now I have to go to the next page. Now you see that there is a property for expectation which says that if a constant quantity multiplies the random variable x, then we can take the constant quantity outside of the expectation sign, and it is exactly similar to this thing. That is, expectation of cx is c into expectation of x. C is any constant. Now you see that here in this case we have the constant quantity as expectation of y because it is a mean, and mean is always constant, so we can take it outside. Here the constant quantity is expectation of x, so we can take it outside. Here both of them are constant quantities, we can take both of them outside the expectation sign. So what do we get? What we actually get over here, I skipped one page actually. So we have this formula, expectation of cx, which is c into expectation of x, and from the previous page we can write as the covariance of xy as, from now onwards we are going to define covariance, denote covariance xy by this thing, covariance xy, cov xy, or you can write it as a sigma capital X suffix capital X capital Y. This will also work. So we actually get expectation of xy. We can take expectation of y outside, and inside x will remain. We can take expectation of x outside, and inside y remains. And we can take expectation of x and expectation of y outside. The product of the two expectations will be taken outside, and what remains inside is the constant quantity 1. Now, you cannot always write, this is not always true. Expectation of xy is not equal to expectation of x into expectation of y always. It is not true always. Under some special condition, it is true. So we cannot do anything with this quantity, but we can do something with the rest of the quantities. So we can write it as expectation of xy. And you see, one more thing is very important. It is that expectation of a constant quantity. Suppose c is a constant. C is any constant number. So expectation of constant is actually constant. Why is it so? It is pretty quite obvious, because suppose I give you a single value 1, and if I ask you, suppose this is in my distribution only 1 is there, and if I ask you what is the what should I say? Let me put it in this way. Suppose I have capital X whose value is only one value is there, 1. And if I ask you to find out the mean, arithmetic mean of X, so what will you write? By the formula, you are going to write 1 by n, summation I goes from 1 to n xi. Now xi is simply 1, and how many terms are there? Only one term is there. So the mean of this single quantity will be 1. So mean is nothing but expectation. So if there is only one constant quantity, its expectation is always constant. Expectation of 1000. If I write expectation of the quantity 1000, it is exactly equal to 1000. If I write expectation of minus 200, it is exactly equal to minus 200. So expectation of constant is always constant. So with respect to that, expectation of 1 will be 1. And thus we get from this step that this is actually equal to expectation of xy minus expectation of xy into expectation of x minus expectation of x into expectation of y plus expectation of x into expectation of y. And these two will cancel each other. So the operational formula thus obtained is given by this. So cov xy is actually given by expectation of xy minus expectation of y into expectation of x. Or you can write it as expectation of x y minus expectation of x into expectation of y, because these are commutative, because these are numbers. Okay, and these are actually real numbers, and real numbers with respect to multiplication is commutative. So this is the operational formula that we can use to find out the covariance between the two variables. If you ask me what is the corresponding summation representation of the formula, so I can say that if for a frequency distribution fi xi, the corresponding formula is as follows: summation fi xi yi minus 1 by n summation fi xi multiplied by 1 by n summation fi yi. So this is the frequency interpretation of the covariance of xy. This is how it is calculated, but we shall not be using the frequency interpretation right now. We'll stick to our expectation notation. Okay, so this is the thing. This is our today's mathematical formula that we are going to use to solve a few problems. Okay, and for this I'm going to take one problem. Its question is the following. Question says that if capital X follows a binomial distribution with parameter n and p, then prove that expectation of x by n minus p whole square, this is equal to pq by n. And next, this is number 1, and the next part that we want to prove is that covariance of x by n minus x by n is equal to minus PQ by N. So we are going to prove this particular result. First of all, let me see what we can do with for the problem number 1. Solution. Now, since X is a binomial random variable with parameters small n and p, we can immediately say that expectation of X is equal to NP and variance of X is equal to NPQ. These are our immediate conclusions from the knowledge of given the condition given in the problem. Now you see that since expectation of X is equal to NP, so what we can do, we can divide both the sides by small n and we get this quantity. No problem with this, it is simple mathematics. Now you see that, just look at this. You see that here the constant term is actually 1 by n. Oh no, this is not the right one. Right formula that I will be using is this one. So you see that here the constant quantity C is actually 1 by n. Here C is actually 1 by n. So we can take this particular constant inside the expectation sign because we know this happens. These two are equivalent. So what we can do, we can take 1 by n inside. We can write it as expectation of X by n. This exactly becomes equal to small p. Okay. So we have got a new random variable X by n whose mean is p. You can put it in this way. Previously, a random variable was there which is binomial whose mean was NP. Now we have defined a new random variable whose mean is actually P. Now carefully observe one thing, that if I write the left hand side of problem number 1, we find that it can be written in the following manner. My left hand side was this, expectation of X by n minus P whole square. Now you see in place of P, we can put expectation of X by n. So we have got expectation of X by n minus expectation of X by n whole square. This is the thing that I am getting. But if you carefully recall that variance of X, as I mentioned in the previous page also, variance of X is given by this formula, isn't it? It is the actual formula of variance of X. So it is actually expectation of X minus EX whole square. Now, if can you you can think in place of X, you can think the variable X and X by n. Okay, suppose you can name this variable X by n to be Y. If we put X by n to be Y, so what we are actually getting? We are actually getting expectation of Y minus expectation of Y whole square. And what is this? This is actually variance of Y, isn't it? It is actually variance of Y. And variance of Y means what? Now let me write in the next page. I'm going to the next page. So variance of Y means what? This is equal to variance of Y means, again you resubstitute the quantity which stands for Y, which is variance of X by n. Okay, but we cannot say anything about variance of X by n because this random variable's probability distribution is not known to us. But what we can do is the following. We can use the following formula. We know that variance of Cx is equal to C squared variance of X. There is a difference between these two formulas. Just try to have a look at it. These two are different. When in expectation, C comes out without as it is, but in variance it comes out getting squared. So we can apply this particular formula over here and we can write it as this is equal to 1 by n. It comes outside the variance sign, so it gets 1 by n squared. We get 1 by n squared, and inside we get variance of X. We cannot know the probability distribution. We may not know the probability distribution of X by n, but we know the probability distribution of X, and we know it is binomial. So in place of variance of X, we can substitute NP Q, and by simple calculation, we are able to show that it is PQ by N, which is the right hand side. Okay, so the first part is proved. Let's talk about the next part. The next part, what we are supposed to prove is the following. What is the left hand side? Left hand side is this quantity. So we are going to start with the left hand side. The left hand side is covariance of x by n comma n minus x by n. So it is n minus x by n. Okay. Now you know the covariance formula. Which formula am I going to use over here? I'm going to use the original one. Original formula is given as this. Let it be in front of you so that you can correlate the thing. So it is expectation of x minus ex, y minus ey. Okay, chat box is open, so please write your roll numbers in the chat box because time is running out. Now what you can do, you can use this particular formula for the random variable this and this. Okay, you can treat this random variable x by n to be, say, capital X, and this random variable n minus x by n to be capital Y. So what comes out of it, we can write, just correlate, just look at this and try to correlate what am I writing. We can write it as x by n minus expectation of x by n, and here we can write n minus x by n minus expectation of n minus x by n. Just see that it is playing the role of y, this is playing the role of x. Now you can do a little bit of mathematics over here, okay, a little bit of calculation. So we can write it as x by n minus expectation of x by n. Let us not touch it, keep it as it is, and we'll do something with the second part. So we can write it as 1 minus x by n, and this is expectation of n minus x by n, so we can write it as expectation of 1 minus x by n. Okay, and then what we can do, we can write the first part as follows: expectation of x by n, expectation of x by n, no problem. In the second part, you can write 1 minus x by n, and you can remove the expectation sign. So it would be what? Expectation of 1 minus expectation of x by n, preceding by a minus sign. So from there we are going to get expectation of 1 plus expectation of x by n. Okay. Why plus? Because here the constant quantity, if you write expectation of minus x by n, so here the constant term is -1, it can come outside the expectation and it becomes -1 into expectation of x by n. Therefore a plus has come out of it. And we know that expectation of 1 is 1. I have already explained why expectation of 1 is 1. So we can write it as 1 minus x by n minus 1 plus expectation of x by n. Okay, so these two will cancel, and from this particular term, you can take the -1 outside, you can take -1 common. So we are taking -1 common and we are writing it as expectation of x by n minus expectation of x by n, and you can write it as x by n minus expectation of x by n, and this can be written in turn as expectation of x by n minus expectation of x by n whole square. And what is it? This is nothing but variance of x by n preceded by a minus sign, and this is equal to, you can take 1 by n outside, so we get 1 by n square, and it is variance of x. And since x is the binomial random variable, you can put the variance formula, which is npq divided by n square preceded by a minus sign, and thus we get minus pq by n, which is probably the right hand side. Just look at it. We have got our right hand side. What is the basis of this particular problem? How can I look at this particular problem? It is a baseless problem. Okay, so I do not, it doesn't have any, I mean, physical significance or physical interpretation. Only objective of letting you do this particular problem is to make yourself comfortable to make you comfortable with the calculation of covariance, so that you can understand how covariance works. Or to put it in other words, you can say that how we can rearrange the terms, and we can bring one particular random variable from the other. And it is very quite amazing to know that if capital X probability distribution is known, we can say that it is binomial. But x by n, we do not know. We cannot write directly what its probability distribution, but we can make use of the fact of expectation, and we can indirectly find out the expectation of x by n. So this is the objective of the problem. Less than 1 minute is remaining. Please join in the next session. Then I'm going to continue for 15 minutes. Okay, I'm stopping here right now. I have saved your chat. Let me wait for the class to end by itself.